Okay, let's pick up where we left off at the end of the last lecture. We were looking at the first law of thermodynamics that we had just gone through some examples and derivations. Essentially, what the first law of thermodynamics is conservation of energy. It says that the change in internal energy within a system is directly equal to the heat you put into the system plus the work you do on the system. Remember now, everything going into the system is positive. And so if you look at our system, the system is something that we've isolated for study. It could be a beaker in the lab that some reaction is taking place. And then there's the surroundings around that beaker. And what the surroundings sometimes most of what we're interested in might be the surroundings of a reaction that's taking place in that beaker in some water. And then for our most of what we're interested in is what's going on in the beaker. But when we take the technical definition of surroundings, it's everything else in the universe. The system plus the surroundings makes the universe. So when I put heat into a system, its internal energy will go up a little bit. And when I do some work on the system, its internal energy will also go up. And this will represent the change in internal energy from the initial state to the final state. It will have increased by exactly the amount of heat and work that we put into the system. Now, I want to illustrate some things with you. Here are all the possibilities. For example, if I'm looking at a system, it's pretty easy to tell how heat flowed during the process and how work flowed. For example, if I'm looking at this as my initial state and this is my final state, here's the system I'm looking at, and here's a thermometer out here outside the system into the surroundings. And this is my final state of this system that's taken place. So I went from this initial state to this final state. In this case, the temperature of the surroundings went up. If the temperature of the surroundings went up, the heat had to come out of the system and go into the surroundings for that to happen. So the temperature increase in the surrounding means heat came out of the system. So Q is going to be less than zero. It's negative. Remember, anything going in is positive, then going out would be negative. Okay, now we can do the same thing for work. Remember, for work to happen, a boundary has to move. If I'm looking at this, there's the boundaries of this system before reaction took place. And here are the boundaries of the system after the reaction took place. So you can see that in going from this state to this state, the system pushed the surroundings back. So the system did work on the surroundings, meaning work came out of the system also. So yeah, if we look at this possibility, I've got the system like this, and if I'm looking at this, it looks like this is the same as what we did a while ago. Okay, heat flows out of the system. Again, it's negative, and see, oh, something seems to be doing funny stuff with me. Let's see if I can back some things up. All right. That's the same one. Well, you know, it might work better if we just look at these. Okay. Now, if I'm looking at this case, the one on the right top, here are the boundaries of the system before the reaction took place, before state one. This is the state 2. And if I'm looking at this, I can see the temperature of the surroundings went down. For that to happen, the heat had to come out of the surroundings and go into the system. Heat going into the system is positive. The work is going to be the same as it was in this one. And going from this state to this state, the system pushed the surroundings back and did work on the surroundings. So heat went into the system, that's positive, and work came out of the system, that's negative. So I can get the sign of the heat and work just by looking at what took place in going from state 1 to state 2. If I go down and look at this possibility, here's my state 1 and here is state 2. If I'm looking at this one, I can see that the thermometer, the temperature went up from this state to this one. So the only way for that to happen is heat had to come out. Heat coming out is negative. So the heat would be negative, and I can tell that by the way the temperature changed. If I'm looking at these two states and I'm thinking, okay, how could I get from this volume to this one? Well, the atmosphere, the pressure would have to act on, push down on, do work on the system. So work going in is positive. If I look at this one, then I can see that the temperature is higher in the initial state than it is in the final state. So the only way that can happen is heat has to come out of the surroundings and go into the system. Anything going in is positive, so Q is greater than 0, it's positive. And looking at this one and going to this volume, I can see the atmosphere had to push down on and do work on, put work energy into the system. Going into the system is positive. So these are the 4 possibilities that you could come up with for heat and work. Looks like I'm in a loop here. Let's escape out of this and come back to where we were. Okay. Okay. Now, we've talked about state functions. Let's look at them again. A state function depends only on the current state, not how it was arrived at. So we don't care about the pathway that's followed. State systems don't, state functions don't change. Here's an illustration of heat and work. I've got a little green box on top of a big can box. And there's 2 ways that box, the little green box, can get down. It can slide down the ramp against some friction forces, or it could fall off the side against no resisting force. And those are 2 different pathways to arrive at the box on the green box on top of the other one and going to the floor. Okay, if we go down the ramp, you can see as we reduce the height, potential energy is going down. The work is going at exactly the same pace going up. It's being used against the friction sliding down that plane. And this would continue until we get the box all the way to the bottom. Now what we would see is the change in potential energy would exactly equal the work that was done. Let's take the other path. As I slide it off the side, okay, I shouldn't have broke it up like that, but hey, I'm too much of a ham not to do it. Okay, well, but the point is the potential energy change was the same. That's a state function, but the work is different. Work had a value going down the ramp, but it had no value when the object moved against no restoring force. So work is not a state function, but internal energy is. Now we define the state of a system with a collection of intensive variables. Now intensive variables are are things that do not depend on the mass or size of the sample. For example, if I measure the temperature of water in a beaker, maybe it's 25 degrees. I could pour out half the water, measure the temperature again, it would still be 25 degrees. If I enclose water at room temperature in a container, its vapor pressure would be about 27 torr. And that would be the pressure of that gas. Well, you know, I could have, as long as I don't change the volume, that I can measure that pressure anywhere in that container I want to. I can measure it at the top or the bottom or the side. I can stick my pressure gauge way down deep. It doesn't matter. It's an intensive variable. Think of intensity. So it doesn't matter how much you've got if you measure temperature, pressure, and the other possible value is a molar volume. You know, the ideal gas equation, PV equals nRT, but if you put the volume divided by N at any constant temperature and pressure, that's equal to R. So you're going to wind up with a constant molar volume, not the volume. The volume itself will change with the amount because the number of moles changes. So the number of moles and the volume change as you increase the number of moles. They both increase, but they both increase at the same rate. So the volume divided by moles is a constant. It is an intensity variable at the constant temperature and pressure. So these are the only three intensive variables for a pure gas system. And we know from the ideal gas equation, we only need two of these three in order to get the other one. Now, internal energy is a state function. It's determined by the intermolecular forces between the atoms and the bonds that make up the molecule. If I've got two atoms bonded together, that has a chemical energy stored in that bond. It also, for a collection of molecules, it depends on the intermolecular forces between the molecules. Now, an ideal gas doesn't have intermolecular forces. We argued that already. But the real gases do have intermolecular forces between particles. So typically, even gases is going to have some kind of intermolecular forces between the molecules. If we're in liquids or solids, intermolecular forces are very substantial. Okay, so we never see absolute energy. There is no measurement you can ever make that will tell you absolutely how much energy a system has. Only changes in energy are observed. We never know exact values. We only know and can measure the difference in values. So if it is a state function, though, and I go from state 1 to state 2, it will always involve the same change in internal energy, no matter how you do it. Remember the little box on a box cartoon we did a while ago? It didn't matter whether we went down the ramp or whether we went off the side. Internal energy was the same, potential energy in that case. So it doesn't matter how you get from state 1 to state 2. Internal energy is the difference between state 2 and state 1. The difference is what we measure. So it doesn't do us any good to say, okay, I measured 100 kilojoules in a process. What was the initial energy and what was the final energy? Well, pick any two numbers you want to that differ by 100 kilojoules. That's a possible answer. So we can't get absolute energies. That's the important takeaway. So delta E is a state function, and we saw from the first law, it's Q plus W. Okay. Now, if you carry out the process so that the boundary can't change in a constant volume calorimeter or in something where your volume can't change. Constant volume calorimeter is called a bomb calorimeter for a good reason. There, you could have some really energetic reactions going on in there, and if it's not heavy enough and sealed enough, it will be a bomb when that process takes place. So um, if you can't move a boundary, no work is done. So the first law still holds, but look at what we've got. If we figure out a way to hold the volume constant, and I just told you, put all your reactants inside a bomb calorimeter so that it can't break apart, and then carry out the reaction. You can measure the heat flow the way we always do. Q is mass times specific heat times a delta T, and we can measure then how much heat flowed during that process. And if the process was carried out at constant volume, look what we got. Remember, Q depends on the path, the way it's done. If I measure a reaction, heat given off in a reaction, if I measure that at constant volume, I will not get the same value I do if I measure the same reaction carried out at constant pressure. Q would change from one to the other, but delta E does not. So that means I just need to do one experiment. I can carry out my chemical reaction inside a bomb calorimeter. I can calculate the heat flow when that volume was constant. That is equal to delta E for that reaction. So I could go in the back of my book and I could write that number down. And if I wrote that number down, it's never going to change as long as I go from that same set of reactants to that same set of products. If I connect the same two states, it'll always be the number I've measured this one time. Now, this is really, really critical that you understand this, that if I measure heat flow at constant volume, I get delta E, and I measured it along that constant volume process. But delta E is a state function, so it doesn't matter in reality whether it's at constant volume or constant pressure. Let's take a real simple example. Suppose I put methane and oxygen inside that bomb calorimeter. I measure the heat flow. And then I take the same amount of methane and I burn it in your Bunsen burner in the lab. I'll get two different heat flows. The one I would measure with the bomb calorimeter, I measured the heat flow at constant volume. That's delta E. So I could take that number and I could write it in the back of the book, remember? So if I've done that experiment and I know, let's say that's 150 kilojoules, that's going in the back of my book. Now I take the same amount of methane and burn it in your Bunsen burner. What is delta E for that change? Well, I can't measure it in the Bunsen burner, but I don't have to. I can go to the back of your book where we wrote it down, and I say, oh, it's 150 kilojoules. I didn't measure it. I didn't have to. I already measured it once. Now, so delta E and going from state 1 to state 2 is the same value, even if the volume is not constant in this process. You just have to do it once in order to know what the value is. So heat flow at constant pressure is also equal to a change in a state function. It's called enthalpy. Enthalpy is delta H is delta E plus delta PV, or P delta V. Delta E is Q plus W. So I can put some stuff together. Delta E is Q at constant pressure minus P delta V. So E2 minus E1 is equal QP. So P minus times V2 minus V1, plug the numbers in, and I get E2 plus PV2 minus E1 plus PV1 is equal QP. Now, that's what we called a state function, wasn't it? Something you can get by just subtracting two numbers. I know this number on the left, I subtract this number here on the right of the equal minus sign, And I get the value of the heat flow at constant pressure by subtracting two numbers. So that defines a state function. E plus PV is defined as a state function, enthalpy. So that's how it's defined. So the heat flow at constant pressure is also gives us a value for the state function. Now your Bunsen burner example, when I measured the heat flow in that Bunsen burner, I measured heat flow at constant pressure. Okay, by definition, that's delta H. Now, I don't know what the number is. I'm going to make up one. Maybe it's 200 kilojoules per mole if I measure delta H. I can put that in the back of the book. Now let's go back and think about the constant volume reaction with the same amount of methane. What's the value of delta H when the process was carried out at constant volume? We can't calculate it. We don't need to. We wrote it down. It's in the back of the book. It's 200 kilojoules. Remember, a state function is a state function is a state function. It doesn't matter how you carry out the process. If you measure it once, you never need to measure it again. Okay. Now, if you put these equations together, you can get a relationship between the heat flow at constant pressure and the heat flow at constant volume. And that's just this. If I take the difference, Q at constant pressure minus Q at constant volume, I get negative work. So the work can be calculated from the difference between the heat flow at constant pressure and the heat flow at constant volume. They typically won't be the same value. Now, both E and H do depend on the type of substance that's present, and actually the amount too. They're not intensive variables, they're extensive variables. So I could have water as a gas, I could have water as a liquid, or I could have water as a solid. So both the internal energy and enthalpy changes if you change from one physical state to another. So it's always important, especially when we're talking about thermodynamics, to note the physical state, because the functions E and H do depend on the physical state. They depend on the amount of substance. If the delta H for forming 1 mole of water from oxygen and hydrogen, I bet you it's about half as much as it is if you form 2 moles. So the amount of internal energy or the amount of enthalpy does depend on the quantity of the sample. A mole is not the same as a gram, so you know that. So the enthalpy for a reaction that involves a mole is quite different from that involves a gram. Delta E and delta H both change signs if the direction of the process is reversed. So if you've got a reaction going in one direction and maybe it gives off heat, if you turned it around and it went, and you imagine the reaction going the other direction, you would get the same heat, but the sign would be reversed. If it's coming out in one case, it's going in the other. Again, for reactions delta E, it would be the energy of the products minus the energy of reactants, but we've already argued we can't possibly measure absolute energies and do that subtraction. So there are ways to do it that doesn't involve that, and that's where we're going now. Now, usually laboratory conditions are constant pressure, so most of the time when we're dealing with heat flow, we're actually dealing with delta H. Now, there is as long as we're dealing with gases, it's fairly easy to hold the volume constant. But if you're dealing with liquids or solids, they have their own density. So when I go from a gaseous sample into a liquid sample, if I fill that container full of that liquid and I start to put some more in it, it's going to explode right in my face. So it's pretty hard to carry out reactions at constant volume if everything is a liquid or solid. Because when I go from one substance to another, its density changes. And that means the volume would either expand or contract. And if it expands and you've got it locked in, it's going to explode. If it contracts, okay, it'll get smaller and there's not a thing in the world you can do about it. You can't stop that. You can't go in there and pull the molecules apart. So the delta H is an easier function to work with in the lab because it's constant pressure, so we don't have to worry about any other problems. Now, the heat required to heat an object is proportional to the mass of the sample, how much it takes to heat 1 gram of it 1 degree, that's the specific heat capacity, and it depends on the temperature change. Isn't that logical? The heat that's going to be required in heating something up, if I had 1 gram or 2 grams, it would take twice as much for 2 grams. If I'm heating a gram of water or a gram of steel, it's going to take a different amount of heat to go 1 degree because each substance, water has a very high heat capacity, big number. And metals are very small heat capacities. It doesn't take much heat to change the temperature of a metal. It takes a lot to change the temperature of water. And it depends on how big the temperature change is. If I'm going to warm it by 5 degrees or warm it all by 10 degrees, it's going to take twice as much for 10 degrees, right? This is all very, very logical. So Q is mass times specific heat times delta T. This is how we actually calculate heat flow. We don't measure heat flow. We measure a change in temperature in a substance that we know its mass and we know its specific heat. Then we measure the temperature. We do the calculation for the heat flow. You can't go in there and count them joules as they come out. You know, that's not the way it's done. Now, sometimes when we're doing the same experiment over and over again in the same container, it's nice to just lump mass times specific heat together since they're never going to change. I can measure it one time. It's called the heat capacity for that system. And if it's a calorimeter, I could just turn that thing up on the bottom and scratch on the bottom what the heat capacity is for that container. And so this becomes a nice way to do experiments when you're doing calorimetry. Oh, you can get the heat flow by measuring the temperature change and then turn the bucket upside down and see what the heat capacity is. And then multiply them together and you get the heat flow. Now, when you put a hot object in contact with a colder one, heat's going to flow and there's not a thing in the world you can do about it. You're not going to stop it. It is going to happen. You can't touch two things together without heat flowing between the two if they're not at the same temperature. And if they're not at the same temperature, that heat will keep on flowing until they both are at the same temperature. So heat that's lost by one, the hot object, is going to be gained by the other, the cold object. If we're looking at heat of vaporization, it's a type of heat for vaporizing 1 mole of a substance. I'm going from the liquid typically to the gas. That's called the molar heat of vaporization. And we can look those numbers up in handbooks and things. If you want to remove heat from an object, you can eventually freeze it. And the heat you have to remove to freeze an object is called the heat of fusion. Now, that's going to be heat, technically in the equation, you're going to have heat coming off when you go from liquid to solid, you know, because you have to take the heat away from it when you do that. I've heard some of the stupidest things people will say. Water gives off heat when it freezes. I'm here to tell you water gives off heat when it freezes exactly the way cows give milk. I grew up on a farm. Cows don't give milk. You have to get in there and take it from them. Okay? If you want to freeze water, water's not going to give you heat. You have to pull the heat out to make it freeze. So if you've heard that stupid thing that hot water freezes faster than cold water, just laugh and go on. You know better. Okay, how much energy is required to stop a 10-gram object moving at 250 meters per second? Okay, these are problems just to look at the units primarily. So the energy to stop would be the kinetic energy that the object has. Kinetic energy is 1/2 mv squared. So we've got to do the 1/2, 0.5. The mass is 10 grams. So we have to have mass in kilograms. 10 grams would be 0.010 kilograms. Velocity is already in meters per second. It would be a messier problem if it was miles per hour, believe me. Okay, but I can put in the 250 squared, and the units have to be squared. And when we do that, we get kilograms meters squared per second squared. That's the energy of joules. So the kinetic energy that that object has is 312.5 joules. That's how much energy it would take to stop it. What mass of water could be vaporized by this much energy? Well, the heat of vaporization of water is 2260 joules per gram. Okay, so let's look at it. Okay, we got 312.5 joules. And now we've got 2260 joules per gram. Multiply those together, and we can come up with 0.138 grams. There's 20 drops in a gram of water. That's less than 3 drops of water. It would take less than 3 drops of water evaporating to supply an energy to stop something moving at 250 meters per second. 10 grams is 2 nickels worth, by the way, the weight of 2 nickels. Weight of 2 nickels traveling at 250 meters per second, that's moving pretty fast, could be stopped by vaporizing less than 3 drops of water. That's how much energy water stores. Okay, let's look at the heat capacity of a system is 20.8 joules per degree. Was heated at constant 1 atmosphere pressure from 25 to 50. Its volume increased from 24.4 liters to 26.5 liters. Calculate Q, W, delta E, and delta H. This will give us a workout on all of these. Okay, let's start looking at them. Q is going to be pretty easily. I just got to multiply the heat capacity times delta T. I get 20.8 joules per degree for the heat capacity. The temperature change is 50 from 25, it'd be 25. It's plus 250 joules. Now I set it up final minus initial, and I came out with the right sign. But does this make sense? Always, always, always check the sign on numbers. I never do that final minus initial. That's what the book tells you to do, always. I'm going to do what my teacher told me in 3rd grade. I'm going to take the big number and subtract the little number from it. And then I'm going to put the sign in. If I'm going to take something from 25 to 50 degrees, do I have to put heat into it? Well, of course I do. Heat going in is positive. So that's how I'm getting my sign. I'm not going to take final minus initial and run the risk that I've got it backwards, okay? I'm going to do the math, and I'm going to check the sign. Now, this was carried out at constant pressure of 1 atmosphere. So Q at constant pressure is directly equal to delta H. So we've got delta H. It's 520 joules, and that is positive. Now, work is minus P delta V. All right, again, we're going to do the same thing. It's at 1 atmosphere pressure. The change in volume, it goes to 26.5 from 24.4. So I get this number. I get minus 2.1 liter atmospheres. And now, that says it's minus 213 joules. And now, how did I get that? I took liter atmospheres and converted it using the ideal gas constant. This 2.1 liter atmospheres, I want to multiply that by 8.314 joules divided by 0.0821 atmospheres. Those are the 2 liter atmospheres. Those are the 2 values of R, and I can use that to do the conversion. That's how I got this 2.13, 213 joules, was I took 2.1 multiplied by 8.314 and divided by 0.0821. And that gave me the unit in joules. I wanted it in joules to compare with these other numbers up here. Now, does that sign make sense? Okay, you heat something at constant volume. What do you expect the volume to do when you heat it up? That's right, it's going to get bigger. So the volume is going to push back the atmosphere because the system is expanding. It's going to push back the atmosphere. It's going to do work on the atmosphere, and work coming out of the system has what sign? Negative. Again, I subtracted it the mathematical way, the way it tells us to do it, but I'm going to always check that sign. Both of these cases, I'd worked the same way. I would have taken the little number and subtracted it from the big number every time. And then I would apply the sign over here. I don't care what my calculator says the sign is. I'm going to assign it myself, always. Delta H is delta E plus delta PV. So I've got a value for delta H. I've got a value for P delta V. And I can calculate delta E now. And if I do that, I get delta E is plus 307 joules. Now, I know I did the math right here because I didn't do a final minus initial. I just plugged values in and did the math. So I'm pretty confident that sign is right. Now, but if I'm going to question the sign for delta E, I'm going to look at the sign of delta H. You know, I don't know of a single case where the sign is different between the two. So if delta H was positive, and I was pretty confident it was, then I'm pretty sure delta E should be positive also. That'll check to see if you did this math correctly. Now, suppose I'm heating a sample of iron. There's the amount, 150 grams. Specific heat of iron is 0.45. Remember, I told you earlier that the specific heat of water is 4.184. So you can see the heat capacity of water is about 10 times that for iron. That's typically what you see for metals. And so I'm going to heat it from 0 up to 0 degrees C to 300 degrees Kelvin. Okay, we got to just be a little careful with our math. Mass times specific heat times temperature change. Okay, so the mass is 150 grams. The specific heat capacity is 0.45 joules per gram per degree. The temperature change, I have to put it in Celsius because this heat capacity is in Celsius. So the small number is 0. The big number in Celsius is 26. Just subtract 273.15, and you get 26.85 as the Celsius temperature. Now my numbers are all good. I can do my math. Units are good. I'll come out with 1810 joules. Now, again, does that sign make sense? Hey, you're going to go from 0 up to 26.85. I think you're going to have to put heat in. That's positive. What will be the final temperature of 50 grams of iron at 100 degrees is dropped into 150 grams of water. Specific heat is 4.18. And the temperature of the water is at 0 degrees. Okay, I'm going to use heat gained equals heat lost. And here again, I'm doing something different than the way the book does it. The book says correctly, it's heat gain equals minus heat lost. I don't like that. It's going to cause you to do a minus of a minus in a problem, and about half the time, students miss that sign. Minus times minus is plus. So what I'm going to do is absolute value. The number of calories given off by some object has to equal the number of calories or joules gained by the other object, the colder one. So I'm going to set it up that way. Now, I had 50 grams of iron. It's at 100 degrees. It's going to go to a temperature less than 100. So I'm going to make this number positive because I know T has to be less than 100. So my delta T is 100 minus T. Here's my 150 grams of water. That's its heat capacity there. Its temperature change. It started at 0 and goes up to a value greater than 0. So T minus 0 will also be a positive number. Now, if you set it up this way, you don't have that minus sign out here, and you don't have this sign this thing flipped around. I'm going to always take the little number subtracted from the big number every time. Okay. Now, from here on, it's just math. Do the arithmetic. You get this. Solving for T, you come up with 3.46 degrees Celsius. Now, you ought to work this problem out and be sure you get this number. It's really critical that you can do this on your calculator to get to a correct answer. Now, does it meet my criteria? Is the final temperature less than 100? Yes, it is. Is the final temperature greater than 0? Yes, it is. So I may have missed it, but at least I know if I made some stupid mistake and I came out with 101, that would have to be wrong. Or if I come out with -6, that would have to be wrong. So I can at least tell some of the mistakes I could have made up here. But if I wind up with a final temperature that's between 100 and 0, okay, it could still be wrong. Here's your checkpoint on these. Okay, here's a reaction of nitrogen and hydrogen to make ammonia. And we carry out experiments. And we've given the heat capacity of the calorimeter. And experiment 1 is going to be this condition. Now remember, it's the same reaction in both experiments. This is experiment 1. The volume is held constant. Volume starts out at 620.4 milliliters. It's still 620.4 milliliters. Changes in temperature goes from 25.00 to 25.25 in the final state. So this is my first experiment, is a constant volume experiment. When you calculate the heat flow, you ought to be able to relate that to one of those state functions, delta E or delta H. The second experiment now is going to be a constant pressure experiment. Pressure is constant, so the volume does change, and the temperature changes in this case. I've got 620.4 milliliters. It goes to 310.4. Volume decreases. Temperature goes from 25.00 to 25.238. Now notice these are not the same values, for the final state. Initial state was the same, but these are not the same final conditions. Okay, but this one's now carried out at constant pressure. Pressure was the same in both of them. So when you calculate the heat flow for going from this initial state to this one, that should identify one of those state functions, delta E or delta H. But which is it? Okay. What I want you to do is fill in all of these values. What is delta H in experiment 1? What's delta E in experiment 1? What's Q in experiment 1? What's work in experiment 1? And experiment 2, delta H is what? Delta E is what? Q is what? And W is what? If we were grading it, I would give a point for each one of those. And when I did grade it, by the way, the average grade was about half of the points. I hope you wouldn't be that like that. Okay. All right. Well, oopsie daisy, something did not happen like it should have happened. Okay, so let's see where we went to. We went to okay, there was the transfer, and we're going to checkpoint 1, so it should be down here somewhere. Okay. All right. I think this is where we should have gone. Okay. All right. Let's pick this back up. Okay. Now, this is what we've learned now about energy and enthalpy. There's no meaningful absolute zero value for them. You only observe differences, and any reference state could be assigned a value of 0 to allow us to do this calculations. Now, I do have a sense that, you know, a system has, say, internal energy, has some value that if we knew this true 0, we could just count the joules up from here to state 1, and that would be the true value of state 1. Or I could then count the joules all the way up to state 2. That would be the energy of state 2 or enthalpy of state 2, whichever one I'm talking about would be the same. Talking about a change in a state function is just this value minus this value. So if I did that, if I take this value and subtract off this value, this is how much is left. Now, suppose I have a reference 0 that isn't the true 0. So true 0 is still down here somewhere. What is this reference? It's something I can define. And we'll talk about it in just a second, but it is a state that is well defined that I could put up in my lab, or someone in Europe could put up the same conditions in his lab, and this state would be defined to be our 0. Now, suppose I'm going to state 1, I need to count the joules from this reference value up to state 1. I could go to get the energy of state 2, I could go from this reference value, just count all my joules up to state 2, then I can subtract them, and I get this difference. Now you see, whether you have the true 0 or whether you have a reference 0 doesn't matter if all you can measure is the left side of this, the change in that function. So the state, it doesn't hurt us at all that we can't have a true 0. We can have a reference 0 that everybody agrees to. Now here's the reference state that we talk about. Standard state is 0. It's for elements. Actually, for chemists, doesn't that make sense? What am I going to do? I'm going to make stuff. What is the stuff made of? It's made of elements. Okay, so if I've got elemental matter, it would be good to call that 0. If I've got oxygen, the way I normally find it at 1 atmosphere pressure and 298 degrees is gaseous. So in the case of oxygen, it would be a diatomic gas, O2, gaseous at 1 atmosphere pressure, 298, that's 0 for oxygen. So the element in their natural phase at 1 atmosphere pressure and the reference temperature, for us, it's 25 degrees Celsius. Over there in Europe, it's a little colder. They use 20 degrees Celsius. No big deal. We can translate our data to their data or their data to ours if we needed to. Okay, but that defines our reference state. Okay, now let's look at a reaction involving formation of barium phosphate. Barium phosphate is a solid at room temperature. And if I imagine this energy of this reaction, or enthalpy for forming this barium phosphate, if I think about forming it from its elements in their reference state, final minus initial is 0. So the heat flow that I might measure in this reaction would be the standard heat of formation for barium phosphate. And the number that you could find in the back of your book is minus 4176 kilojoules per mole. Now, can we actually carry out that reaction? Probably not. Let's illustrate something else now about the standard state that's really, really critical. Here's a different reaction. Ammonia and oxygen can be oxidized to make nitrogen dioxide and water, and these are all gaseous. Now, you can calculate it from the standard heats of formation. It's going to be 4 times the heat of formation of the NO2 plus 6 times the heat of formation of water minus 4 times the heat of formation of ammonia, and the standard heat of formation of the oxygen is 0, so we can leave that out. We put the numbers out of the back of the book. We can calculate the energy. The change in enthalpy would be minus 1136.76 kilojoules for forming 1 mole of that compound. So that would be the heat of that reaction. It would be released to the environment when 4 moles of ammonia is oxidized. Now, does the sign make sense? It does to me, because when you burn anything, when you oxidize anything, you give off heat. So it should be negative, and that's what we observe. Now, I want to show you what we're talking about, a standard state. And perk up. If you're getting a little sleepy, wake yourself up right now. This is important. Okay? What does the standard state look like? It's got to have 1 atmosphere partial pressure of ammonia. That's the standard state for ammonia. It's got to have 1 atmosphere partial pressure of oxygen in it. Even though we didn't use it in that calculation for heat flow, it's still a component in that system. The surprising thing to some people is the standard state also requires the products to be in it. Now, normally we don't carry out a reaction where we start with a set of reactants and we start with some product already. We don't usually do that, but that's what this is stating. We are going to have 1 atmosphere partial pressure of NO2, and we're going to have 1 atmosphere pressure of water vapor. These are all gases. So the standard state requires 1 atmosphere pressure of ammonia and 1 atmosphere pressure of oxygen, 1 atmosphere pressure of nitrogen dioxide, and 1 atmosphere pressure of water vapor. Total pressure would be 4 atmospheres. Now let me remind you of what we did with Raoult's law. If you want the mole fraction of some component, you take its pressure and divide by the total pressure. So this standard state is going to have 1/4, 0.25 mole fraction of the moles present is ammonia, 0.25 mole fraction of the molecules present is oxygen, 0.25 mole fraction of NO2, and 0.25 mole fraction of water. So when we talk about a standard state set, we're talking about a certain fixed set of concentrations. That is critical. We're going to cover some of this kind of stuff very early in Gen Chem 2. And you've got to understand that when we're talking about the standard heat of formation of involved in a reaction, we're talking about a certain set of concentrations. And when the reaction continues, it might continue from that set on to make more product, or maybe it could take the products and go back toward reactants. We'll learn how to decide which way that happens later. But the critical thing is you got to know first that you're at a certain fixed set of concentrations. 0.25 mole fraction, 0.25 mole fraction, 0.25 mole fraction, 0.25 mole fraction. And then you could understand how we can determine which direction a reaction might go from there, because we need to know where there is. Now, what does that mean? It means the container has to be so large that I could remove 4 moles of ammonia from it, and I wouldn't even change the mole fraction out in the 10th decimal place. That would have to be a pretty big container. I could remove the 4 moles of ammonia. I could remove the 7 moles of oxygen. I could add 4 moles of nitrogen dioxide and add 6 moles of water, and it doesn't change the partial pressure or mole fraction of anything because the container is too big. Now, is that something we can do in the lab? Of course not. Who cares? Initial state, final state, remember? Doesn't matter whether we can actually do it or not. We can calculate what it would be if we did. So the total pressure is going to remain 4 atmospheres in that, and the mole fraction of each one is 0.25. Now, the book does not tell you this. What the authors say is technically true, but the clear implication is that the reaction is taking place at 1 atmosphere pressure. It is not. The reaction is taking place at 4 atmospheres total pressure. That is a big problem, and I've not seen one textbook that did it correctly. So, but this is true. Believe me, it is true. This is my area of expertise. This is true. Standard state fixes the specific set of concentrations, and that is very important. Remember that. Okay, now in this reaction then, we would be talking about, suppose I'm talking about standard state. Well, it's not a big deal here. I've got to have some solid barium. I've got to have some solid phosphorus. Notice it is P4 is the standard reference state for phosphorus. It is oxygen gases, and this is a product. So actually it's only going to be 1 atmosphere pressure in this reaction because the oxygen is the only one that's a gas. But I'm still carrying out a reaction in such a container so large that I can get rid of those 4 moles of oxygen and the pressure doesn't drop, stays the same. Okay, let's back that up. I didn't remember whether I clicked on that or not. All right, let's recover. Okay, now the enthalpy of a reaction involves a number of steps. The sum of the enthalpies of each step is the enthalpy of the reaction. Hess's law, you just did 2 labs on that. Okay, if the direction is reversed, then the sign of the heat flow is reversed. If a reaction is exothermic in one direction, it's endothermic in the other direction. Okay, we're over time, so if any of you need to leave, it's okay. We'll continue till I finish this lesson, and then I'll stop the recording. You know what? I'm not going to do that. I'm going to stop right here, and we'll pick up Hess's law on Monday. So let's escape from here, and let's we will